welcome to your first Learning with Funke video. Today we're going to be talking about the golden section method as requested from my chemical engineering students. Just a quick background. We'll be going over what the golden section method is, as well as the algorithm to how this works. First of all, what is the golden section method? The golden section method is an optimization tool. We use it for determining the maxima or the minima within a given interval. And pretty much the way this method works is that it works by reducing your initial search interval and zooms in to your interval of interest until it finally gets your desired maxima or minima. So you are pretty much eliminating regions while retaining the maxima or minima of interest, and that's how golden section method works. And so you might be curious as to how this, why is the golden section method important? But what we've come to find out is, this golden section method has been found to, be applicable in some of these diagrams that you see on the screen. So the Parthenon, the pyramid, even your hand, and the design of the credit card. So softwares like MATLAB will commonly use algorithms like this to determine what the optimum, your minimum or your maximum for a function is. So it's good to learn about it. And so how this works is, like I was saying before, it uses a golden ratio, which is given on the screen here. And it works by dividing your interval into parts based on the golden ratio. You might have also heard about the Fibonacci series, which is like a series of consecutive Fibonacci numbers. And what we've come to find out is this Fibonacci number tends to the golden ratio as n goes to infinity, and I will show you on the next screen. Okay, so for the Fibonacci series as provided on this screen, if you take the ratio of these two numbers, what you'll find is 1597 divided by 987. You'll see that number tends to go towards the golden ratio, and that's how they're similar. And for a general example, we'll be going over, how to, perform this algorithm on a maximization example as well as a minimization example. I've provided a function here which we'll be going over, and just to check, you can always use the graphical method to confirm that whatever you've arrived at with your golden section method is actually accurate. And so to begin, I plot, and you can see on the next screen that you can see that you have a maxima at about 0.44, just slightly less than 0.45 for your function. And your tau, which we can take as our x in this case, is about 0.4, between 0.4 and 0.45. And just, here we've also set the tolerance for an objective function of 0.01. I'll be going over what this means as we go over the video. So just, stay tuned and let's learn together. Okay. So how do I use the golden section method? Now I'm going to be talking about the method algorithm for using the golden section method. Just quick reminders. I've talked about, how we use the phi, which is the golden ratio. And in this case, for the golden section method, we're going to be using a very similar number that's related to the golden ratio. I'm going to call it lambda. Lambda is just phi minus 1, and it's 0.618. And this number we'll be using to generate some numbers on our table as we find the optimum, minima or maxima for our functions. Okay, so how does this golden section method work? So first of all, your golden section method works on some assumptions. So for the first case, you have to have one minimum or one maximum in your range. Otherwise, it's pretty much, gives you one of them. It doesn't give you like all reported minimums or maximums. It will just report one of them. And then the second case is that you have to have a starting range of X. So given like a range A to B, where that minimum or maximum is going to be within. And so here, as you can see, I have the first step is that you identify your range AB. And then within that range AB, you have to calculate your M and your N based on that lambda that I showed you before, which is related to your golden ratio. And then after calculating A, M, N, and B, you would then evaluate the function that you're given, whose extrema, minimum or maximum you're trying to find at point A. So you would have an f of A, an f of M, an f of N, and an f of B. You might be wondering, how do I find my M and my N? Well, these are the formulas you would use to calculate your M and your N points, where lambda is that 0.618 that I showed you before, and your B and your A are just, your N points for that, your range. Same thing for the next step. You now, based on whether you're following the maximization or minimization algorithm, you would have different approaches to solving the problem. So let's take a minimization algorithm, for example. Say I have a range A to B, right, that contains my points M and N, which I have now calculated. If I'm trying to minimize, think about it this way. If you're trying to minimize a function, clearly you don't want, high numbers. You want to find the minimum point of that function. And in that case, in a minimization scenario, what you're thinking about is you don't want the maximum point, so you're eliminating the points or the range that has the maximum point. Similarly, when you don't want the minimum point, when you're doing the maximization, you're eliminating the region that has the minimum point. And that's pretty much how this algorithm works in terms of what region you need and what region you have to reject. Okay, so in this case, I've stated here that for a minimization algorithm, how would that work? So say I had a range AB, right? And then if f of M, right, let's assume f at this point M is less than f at this point N, which side are we going to reject? Well, clearly, if you're trying to minimize, you know that your f of M gives you the smaller point. So you want that smaller point. You want to reject the bigger point. So in that case, you will reject this right-hand side. And what that means is you would end up crossing out this right-hand side, which is like the f of B. And then now you're left with a smaller range, which goes from A to N. In similar scenario, let's say your f of M was actually, your f of N was actually smaller, and you wanted the smaller side, then you would reject the left-hand side. So what does this mean? This just means when you're minimizing, you're rejecting the side that has the higher number. And usually you would have to reject either the left-hand side or the right-hand side. You would never have to reject the center, right? And that's how golden section method works. So in that case, let me wipe this off the screen. So in that case, if f of M is less than f of N, you reject the right side, like I said before, because we want the smaller number. And your N in your next algorithm now becomes your new B point. Your M becomes your new N point. And then you have to calculate your new M point. So the way I used to think about it as an undergrad was I would literally just, know that I'm moving 2 over, and then the third number I have to calculate, while the side that doesn't move at all or that doesn't get rejected, which is this side in this case, stays the same. Hopefully that helps, but if it doesn't, we're going to go over something that's more visual for those of my visual learners, so it's easier to understand. Okay. And now let's go over the second scenario. We've gone over this scenario, but what if f of N is less than f of M in the minimization scenario? Well, I went over this and I said, well, we want the smaller side in the minimization scenario. So in that case, what side am I going to reject? I'm going to reject the left side, right? Because if I want the smaller side, and because f of N is smaller, definitely I want to keep the right side because that's where I'm interested in. And then the bigger side gets rejected. Note, this is for a minimization scenario, right? It will be flipped for the other case if it was for maximization. Okay, and now if we've rejected this side, what happens? Your M point in this algorithm will become your new A point, right, in your next algorithm. Your current N becomes your new M point in your next iteration. And then you have to calculate it. Your new N point, kind of like think about how I said you move 2 over and then you calculate the third point. So if you're moving this over, clearly in your new algorithm, you're going to calculate the new endpoint. And this doesn't change, so this stays the same. All right, so now let's go into a more visual approach to learn this. And let's take this minimization scenario, for example. We have this range A goes to B, A through B. And what we see here is, let's assume our f of m were less than our f of n. And then in that case, you know, okay, I'm in a minimization scenario. I want my smaller numbers. So what point do I reject? I have to reject what? The right side, right? Because if f of m is less and I'm trying to minimize, I want to keep the left side. I want to reject the right side. And so how that works is you would reject this side. And then in your next algorithm, what would happen is your n point becomes your new b point. Your m point becomes your new n point. And like I said, once you've moved 2 over, you calculate the third point, which the formula for the m is given above, and your a point will stay the same. Now let's go to the next scenario, right? What if your f of n is less than your f of m? In this case, if your f of n is less than your f of m, right? So now this number is smaller. So what do? I want the smaller side, right? So what side do I reject? Now I reject the left side. And in this case, what happens is your m point, right, becomes what? Your m point becomes your new a point. Your n point becomes your new m point. You calculate the end point, your new end point, and then just because you didn't reject this side, your b point will stay the same. Okay. And why this happens to be very efficient is, if you were doing this on hand, you know, you wouldn't have to do this on hand typically, because MATLAB typically goes through these algorithms pretty fast. But if you were giving on an exam like I was and you had to do this by hand, what you will find is, for each iteration, you're literally only calculating one thing. Well, maybe two things, right? Because you literally only have to calculate either m and f of m, or you would have to calculate n and f of n. Okay, now let's go back and see the opposite for the maximization scenario. So once again, you're saying for the maximization scenario, you have one maximum in that range A to B, kind of like we talked about before. And now think about it. We want the maximum in the range. So when we have a smaller point, now we are rejecting that smaller point, if it's on the left side or the right side, based on if it's an m or an n, right? Now let's see. So if we have f of m, your function is less than f of n. So here, this function f of m is less than f of n. Now remember, now we're in the maximization scenario, correct? So we don't want the smaller number, we want the bigger number. In that case, we want this number here. And since we can only reject the left or the right side, which side are we going to reject? We're going to reject the left side, right? And kind of like how we went over that algorithm before, we're going to go over that again. But when you reject the left side, now what happens? Your m point becomes your new a point because you've rejected this side, right? Your n point becomes your new m point, and then you calculate the new end point, and your b stays the same. All right. What if f of n, in this case, was actually less than f of m? So in this case, right, if this was less than your f of m, what side do you want to reject? In this case, you want to reject what? So we're saying now it's f of n is less than f of m, or f of m is greater than f of n, right? So you want the bigger side, right? So clearly this is smaller, so you reject the right side, right? And now in this case, is you've rejected the right side, this you don't have this number anymore because this goes away. You remember, you're closing in on the extremum point, so you're pretty much eliminating regions till you zoom into the maximum or minimum that you want, in this case the maximum. So once you've eliminated the b point, right, kind of like how we went over in the last couple slides, your n becomes what? Your new b point on the next iteration. Your m becomes your new endpoint. You have to calculate the new endpoint, but since you didn't eliminate this region, your a will stay the same, right? Okay, now let's do this again here for the maxima until it will make more sense. Okay, once again, we start with our a to b range, and what you see here is, if f of n is less than f of m, like we said before, because this is less for a maximization problem, we want the higher side. So we're going to be rejecting the right side, right? Okay. And so when you reject the right side, what happens? Remember how we said now your end point becomes your new B point. Your end point becomes your new end point. You're moving 2 over, right? And then you calculate the third point, and then the last point stays the same. Okay. And now to calculate your end point, you would just use this M formula shown on the screen, and then you would have to calculate f of m, given you already know the function that you're trying to, maximize, because that will be provided to you. So what you're doing is you're just plugging in that endpoint as your x value, or your independent variable into your function to get your f at that point. Okay. Now let's flip the scenario. What if f of m is less than f of n? Remember, once again, you're trying to maximize, right? So you're eliminating what? The left side, because that's the smaller side, right? And then m, in this case, right, becomes your new m. Your m becomes your new a point, sorry. Your n becomes your new m point. You calculate your what? Your new n point. And then once again, the other side stays the same because we didn't eliminate that region. So b stays the same. Okay. Now we've seen a bunch of these examples. Let's go and actually start solving a problem, the problem that we provided before for a maximization example. So I've done this in Excel to make it really easy. But what I did was I knew my A was in the range 0 to 2 as provided at the beginning of the problem. And what I did next was I calculated my M and my N points based on the formulas that I've shown in the previous screens. Okay, so after calculating my M and my N points, all I'm doing here is I'm calculating my Z, right, which is my CB over CA naught, right, because that's my objective function here. And I'm just plugging in. We said K1 was 1 and K2 was 1 and K1 was 3. So once I plug all those values in, here my tau is my X, right? So when X is equal to 0, I plug that in, I get my Z point, which is 0. When X is equal to M, which is 0.76932, I get my Z here. Same thing, I plug this in, I get my new F, my F at that point, plug B in, I get my F at B. Okay, now from what you can see here, we've gone over the visual examples, but let's take a look at it, how it works in Excel. So from what you can see here, you can see that looking at these Z points, right, if my objective is to maximize, we see here clearly that F at N is smaller than F at M. So if I'm trying to maximize, you already know that I'm going to keep this F at M, which is on my left side, but eliminate the right side. Eliminating the right side, like I said before, involves either eliminating the A region or the B region, right? So now we're just going to eliminate this side because this side has the smaller number. And that is why here I have my Excel sheet that programs it for me, and it gives me that I'm rejecting my right side. Okay. Now, that's for the first situation, right? And then when we start to go to the second iteration, remember how I said things move 2 over? Well, that's exactly what you see here. So you see here that my N becomes my new B point, right? My M becomes my new N point. And here, what am I doing? I'm recalculating my new M, giving the formula for the M that I provided. And this is literally staying the same. So this kind of shows when I talked about how, you're only calculating one thing for every iteration, right? The M and that function at that new M value. Okay, and that's for the example for the right side, but I better show that here on the next slide. You see how I said we reject the right side, right, which is this B point, right? This N becomes what? Your new B, right? Exactly. You don't have to recalculate that. This M and its value becomes your new N. You can recalculate this M value based on this formula given here, and then this A stays the same. So now that I've done this first iteration like I talked about, the next question now is, okay, we've done iteration 1. Now we have to go ahead and do iteration 2. Then I'm going to do exactly the same thing and look at this range and say, okay, in my f of m value and my f of n value, which one is higher? Because I really want to keep the max, right? So if I'm going to keep the max, I have to keep this point, which is on my left point. So once again, I'm going to eliminate what? The n to the b region, which is like the right side, right? So now I'm eliminating this region again, just like before, and I'm doing the exact same thing, right, as here. So since I'm eliminating the right region, your n becomes your new b point. So you see here, this same n value comes here, becomes your new b point. Your m value, right, exactly comes here, becomes your new m point. You're calculating the third point. You've moved 2 over. You calculate the third one, giving your m just like before. And then your a stays the same, right? All right. Now, let's go to the next slide and see how the eliminating the left side works. So we've done these first 2 iterations and we're here now. When we go to this next slide here, now we look at, we're at this point, right? We're trying to go to iteration 3. So now what we are seeing here now though is that in this range, remember, we are still doing the max. It's still a maximization problem all through, right? We're trying to keep the maximum point. But what do you notice? You notice here that your maximum now is at f of n. Since I'm trying to keep the maximum point because this is a maximization problem, I'm eliminating what? The left side, right? So the side below m, right? Anything between a and m. In that case, you have to eliminate this side because technically speaking, you can only eliminate this side or this side, right? So since I'm keeping this right side, I'm eliminating the left side. And so what happens now is similar to how we've been doing it before, but in this case, it's just on the other end. What happens is now you see that this m becomes your new a point. We're moving 2 over. This n becomes your new m point, right? This is your new end point. This would have to get calculated, kind of like how we see on the screen here. And then you will just calculate that using this formula, right? Where n is equal to a plus lambda, b minus a. And once again, because we did not eliminate this right region, you see that this stays the same, right? If we kept doing this on and on, I'm going to show one more example here. But let's say we're going from iteration 3 now to iteration 4. What we see here is after we've calculated the new points, right, after moving things over, now I have to do the same thing again. I look in this range and say, where do I have my maximum function, right? I see between m and n, you're always evaluating between m and n. You see here that what? It's higher at m. So definitely it's higher on the left side, which I want to keep because that's my maximization, right? I want to keep the maximum point. So here, which side am I eliminating? I'm eliminating the right side. And so since I'm eliminating the right side, this, right, goes here. Your endpoint becomes your new b point. Your m point becomes your new endpoint, right? Once again, you move 2 over, you're calculating the third point, you're calculating your new endpoint, right? We've given that formula here on the screen. And then what happens to your other end, your a point? Your a point will stay the same. And so what would happen is you would literally keep doing this, you know, in so many iterations. I remember for this problem, I did up to, I think, 9-10 iterations. But how the next part we have to go over is how do we know when to stop? Right? So technically speaking, if you program this in, or like how MATLAB or like other softwares work, is that they have some kind of tolerance, a very small tolerance, which is like points, it could be like 0.0001 or 0.001. In this problem, we're giving 0.01 because we're doing this by hand. So it's not exactly as accurate, but tolerance could be based on convergence or based on the differences in your objective function from the previous table. But for ease, I think for the most part, people just look at the differences between your m and your n values. So what do I mean by that? So now we're just looking at how close, right, are these two f of m and f of n values? Is it close enough that it's between plus or minus 0.01, which in this case we see that it is, right? Because the difference between 0.444438 and 0.439136 is in the range of plus or minus 0.01. So in this case, we can say, okay, I've hit my termination criteria. I can stop now because I know that this is, you know, pretty much close to the max I can get for this problem. And so based on that, we will see that just by looking at these two numbers, right, we know that whatever our maximum value is, it has to be pretty close to 0.44438 at an x value of at about 0.403 approximately. And just to confirm that using the graphical method, we see that that confirms it, right? Because we see here that we have a z max at 0.444 and x is 0.405. Once again, let's go back. We see we had a z max at 0.444 with the x at 0.403. It's pretty approximate, right? We see that from doing this golden section method, by closing in on the extrema of interest based on whether we want to do a maximization or a minimization, we pretty much hit, the optimum that we'll pretty much get from using the software or other using a software like MATLAB or other softwares, right? So we've gone, pretty intense into the maximization realm. Let's look at another maximization problem. This one you can practice yourself and see that you get what I have. But once again, I've done this in Excel. You see here, after, first thing, like I said, you have your A to B region. You find your z points or your objective functions by plugging in the x into those into your function, and you get what your z points are. And then, after you've calculated your m and your n using the formula provided earlier, and then from there you're literally just following the same iteration over and over, finding which function, whether it's the left or the right side that maximizes your problem. This is a maximization problem. So let's take a look at the first two. So here, once again, we see f at m is 1.3755. F at n is 1.1853. So what we want to do here, of course, is that we're going to reject the right side. And then what happens? This moves over 1. This moves over 1. So your endpoint becomes your new b point. Your endpoint becomes your new endpoint. Like I said, you move 2 over, you calculate the third point, and then this stays the same, right? Now I do the same thing, right? And that's pretty much why you see it says eliminate the right region here. I do the same thing for iteration, going to iteration 2. We see here that the f at m is 1.4448 and the f at n is 1.3755. If I'm trying to, keep the max region, once again, I'm eliminating the right region, and I'm literally doing the same thing. This moves over 1. This whole point moves over 1. This whole point moves over 1. I'm calculating the new endpoint, and my A stays the same, right? All right, now let's go from iteration 2 to iteration 3. Okay, so now here, if I'm trying to go to this new point, let's see. I evaluate this point and this point. I see that this point is, slightly higher than this point, right? Because 1.4448 is higher than 1.4446. So what does that mean? I'm trying to do a maximization problem, right? So I eliminate the left side. And in that case, what you see here now is, since I've eliminated the left side, right, things kind of fall in place to fill in that eliminated spot. So here, M will go here, right? Move over 1 to become your new A. N will go over here, become your new M. You calculate the third one, your third point, and then your B stays the same since it was not eliminated. And you literally keep doing that over and over and over until you hit your termination criteria, where your difference in between f of m and f of n is pretty close, that you can say it's not significant, sorry. So here, points, I'm trying to look for something that's about 0.01. That's, I think, by the time I got to iteration 5, it was pretty close. So I said, okay, my max is going to be what? This is still higher, so I said my max is going to be at about 1.45 when x value is about, so when your x value is about 0.2. And if you see, when I graph this, you pretty much have that your z max, once again, is about 1.45. Your x value is about 0.19, which is close enough to 0.2. You can consider that accurate enough. But if you're doing this on the software, like I said earlier, this would be pretty damn accurate, very close to your optimum. And if you continue doing this over and over again, obviously, you just, as small as a tolerance as you can get, you're going to start to hit these numbers. We're just stopping very close because, our tolerance defines that, at 0.01, we can stop, right? And that's why we're not exactly hitting these numbers, but we're very close. All right, so we've done a lot of maximization examples. Let's look at the minimization example. This is a minimization example. I've picked a very simple minimization problem, graphed it first. So you see here that when you graph it, right, you have your minimum at x is equal to 3. From calculus classes, you would know that, it's just your x squared moving over to the right 3 units. So that makes sense that, if your x squared value has a minimum of 0, 0, your x minus 3 all bracketed squared should have a minimum at 3, right? All right. And so based on this, if you did the same thing, right, now we're switching over to a minimization, right? You have to remember now we're no longer doing a maximization problem. So since we're switching over to a minimization problem, we're trying to get what? The minimum in every iteration. Okay. So knowing that, I look at these points. First of all, I have my A. It gives me like my A range. So from 0 to 4. So your A is 0 and your B is 4. I've put those numbers in. And next thing I would have to do is, well, calculate my M, calculate my N, given those equations that take in the A value and the B value and your golden, your lambda value related to your golden ratio. And after that, what's the next thing I'll do? Once again, like I said before, you calculate, plug this number into your function to get your objective function z, in this case, which is equal to f, right? Your objective function f of x is equal to z. And so when a is 0, we see that what? That gives us minus 3 squared, right? When a is 0, that gives us minus 3 squared. And that's equals to what? Minus 3 squared, which is just what? 9, right? So literally you can say I'm just plugging these numbers into my function to get my z. I do the same thing for my m. I plug in x as 1.527864. I get that my f of x or my z is this number. And I pretty much do the same thing for everything else and I get these numbers. Now, after plugging in all my numbers, I start doing the iteration algorithm all over again, right? So now I'm saying, I look at all these points. I'm trying to find the minimum point, right? So obviously, I want the f of m or the f of n that gives me the smaller number. So if you look here, you wouldn't pick this point, right? Because this gives you a larger number, but you're trying to minimize. So you would pick this point. So this is what you actually want. And in that case, that means you're keeping the right side because n is on the right side, right? And you're eliminating what? The left side. So now we eliminate A. And once you eliminate A, we went over this before, but going over it again, this kind of moves over, right? Fills in the spot for the A. Your M becomes your new A point. Your N becomes your new N point. You calculate the third point because you've moved over 2, and then this stays the same. Now we've done the first iteration, right? Now we'll do the same thing again for the second iteration. We're going from iteration 1 to iteration 2. I look at these two numbers and I say, okay, I want the smaller number. Clearly 0.003106 is smaller than 0.27864. So I want to keep this right side because it has a smaller number and I want to eliminate the left side. And so once I do that, what happens is, once again, you're doing the same thing. This moves over, this whole thing moves over. So your x is now this x, your z is now this former z. So your m becomes your new A point. Once again, your n becomes your new n point. You're calculating the third point, right? And your b stays the same. Once again, I get here now at iteration 2 going to 3, and I say, okay, I've calculated my new endpoint. Now let's look at which region do I eliminate here. Now I want to keep this region, right? Because it has a smaller number at f of m than f of n, right? F of n is on the right side, so I'm going to eliminate the right region. That's why I have it saying eliminate right here. And then pretty much just doing the same thing. Now this goes over here. Your n becomes your new b point. Your m becomes your new endpoint. You calculate your m point using that formula and then find what f of m is at that point, and your a point stays the same. All right, now speeding things up a little bit, you do the same thing here, right? What point are we going to eliminate here? Clearly, you want to keep this point, right? Because it's smaller, so you're eliminating the left side, right? Because f of m is smaller, so you eliminate the left. F of m is bigger, so you eliminate the left side. And so when you eliminate the left side, what happens? You're pretty much doing the same thing again. This moves here, this moves here. You calculate this new endpoint using the n formula, and then you calculate the f at n, and then this stays the same, right? Okay. Now you get to iteration 4. We've written a lot on the screen, but now you're at iteration 4. And at iteration 4, now you're saying, okay, I'm still doing the same thing again. I'm looking for the smaller number because I'm doing a minimization problem, right? This is smaller. I want to keep this side, which is on the left side, and eliminate the right side, right? That's why this is eliminate the right side from Excel programming, and everything kind of moves over to fill in the eliminated side. So this will go here, this will go here, right? And then what happens, you calculate the third number, and this stays the same. So when you do this over and over and over and over and over, what do you see? You see that your number starts to approach what? You see that for each iteration, you're literally approaching the point where you're having 2.97. Just looking at iteration 5 here, you see you're very close to x is 3, right? Because you have 2.97 and 3.055. So you know your range is pretty much somewhere in between these. You could take the average of these two numbers, or you just keep going. If you hit your tolerance, and you say, okay, you know, this is sufficient enough, I can take, you know, this point and like the z value at that point, you can pretty much see already that your x will start to approach x is equal to 3 with an f min that is at about 0. And that's pretty much how, you know, the golden section algorithm works. And so today I hope you've been able to learn the golden section method, its real-life applications, the golden section algorithm for both maximization and minimization with the examples that I've gone over. Special thanks to Dr. Shuram for his lecture examples covered in these slides, and as well as the students who have requested for this video. And if you have any questions, please feel free to reach out to me at learningwithfunke@gmail.com, and I'll be happy to answer. Thank you very much, and see you in my next video.